Imagine a rabbit chasing a dog. Your mental image will look something like this. However, when asking Google to find images of a rabbit chasing a dog, it returns dogs chasing rabbits. Searching algorithms treat a sentence as a bag of words, and since dogs chasing rabbits are more common, that's what the search comes up with. Google's algorithms are improving, but computers are still far from correctly interpreting human language. So how can we teach a computer the meaning of a sentence? Human language is a carrier of information that one person wishes to convey to another. Sentences combine words in such a way that together they mean precisely what the sender has in mind. So a sentence is not just a bag of words, but rather a process that takes the meaning of individual words and produces the meaning of the sentence. So to teach a computer the meaning of a sentence, we need to teach it the meaning of words and describe how to combine those meanings to get the meaning of the sentence. Let us first focus on the meaning of individual words. Teaching a computer the meaning of a word seems straightforward. Just give it a dictionary. However, suppose you didn't know what a chair was, and I gave you a description, something like a thing made for one person to sit on. Would that be enough? Is a stool a chair? And what about a swing? Is that a chair? This is not the way children learn the meaning of words, and it isn't very suitable for a computer either. A practical way to learn what is and what is not described by the word chair is from the context in which the word is used. We use this idea of contextual meaning to teach a computer the meaning of a word. We give the computer a list of, say, the 2,000 most frequently used words. To compute the meaning of a new word, the computer measures how often it appears close to the words in the list. To a computer, the meaning of a word is then a list of numbers, each number representing how similar the word is to one of the words from the list. The lists representing chair and stool will be very similar, while the list of ink and fridge will look nothing like each other. Now that we have the meaning of individual words, we need to combine them into a sentence. We think of the different parts of the sentence behaving as processes, modifying the meaning of individual words. Nouns are the basic inputs of our sentence. We draw them as processes with no input and as output the meaning of the nouns. Adjectives modify a noun, so we can draw them as processes that ask for a noun as input and return a new noun. Connecting the output of a noun to the input of an adjective produces the modified noun. A transitive verb is a process that takes two nouns and forms a sentence with them, so the output of this process is of a different type than the output of an adjective. Notice also that it is important not to swap the two inputs of a verb, as this influences the meaning of the sentence. Each grammatical type has its own process diagram, depending on its function within a sentence. We can combine different processes to form more complicated sentences, but how does a computer turn a sentence into such a process? We can make the process look more like a sentence by putting all the boxes in one line and moving the inputs to the top of the boxes. The only thing a computer now needs to turn a plain sentence into a process is the grammar of the sentence. The grammar indicates which words of the sentence are nouns, adjectives, and verbs, so the computer can allocate the right process to each word in the sentence. The grammar also tells the computer how the different words in the sentence are related to one another, so the computer can connect all the wires and build the final process. So the computer has the meaning of words, which are long lists of numbers, and it can build a process representing the sentence. The process then tells the computer how to manipulate the word meanings to compute the meaning of the sentence. By the way, these process diagrams are not things we just made up. They are used in quantum theory. The computations that we apply to manipulate the meanings of words are the same computations that are applied to quantum particles when they are manipulated, for instance, by a quantum computer or in a physical experiment. Wait, so mathematics from quantum theory can be used to compute language meaning? That's right. Human language and quantum theory are not as different as they may seem. Our research exploits this similarity, for example by using density matrices to model ambiguous words. Using the mathematics from quantum theory, we try to capture how humans understand language, so that a computer can do so too.